The binomial expansion of polynomials is just multiplication. And so here we have the multiplication of binomials. And this a plus b, it's just multiplication. It is a plus b times a plus b, right? That's all this is. I'm sorry, my handwriting spazzed out there a little bit. Okay, so if we multiply this, it's just distribution. This is distributive property of multiplication. That's how you multiply binomials together. So this is going to end up being a squared plus 2ab plus b squared. And I apologize, I didn't write out both of the a b terms. I just added them together because I knew there was going to be two. Okay, so I skipped that step, but I think you are hopefully still with me. All right, if you do a cubed, a plus b quantity cubed, a plus b times a plus b times a plus b, well, same thing. The way you would probably do this is to take these two and multiply them together, and then once you have that, multiply that new, what would be a quadratic. In fact, this, right, if we multiply this by a plus b, that would be what we would expect to put for this answer. So what we're going to put then, this answer is going to end up being a cubed plus 3 a squared b plus 3 ab squared plus b cubed. Right, that's what that answer is going to end up being there. And then if we do this one, this is just a plus b times a, times a plus b times a plus b times a plus b. There you go. This will be a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. And so those are how these things expand. Now, I did a couple more. So let me show you what those would look like. So when you expand these, you can observe something here with the coefficients of each term. And if you haven't seen this before, what's produced here is something called Pascal's triangle. In math, Pascal's triangle has all these really neat applications. It comes up from binomial expansion, but then there's all these other things, and it's all related. There's not just coincidental that Pascal's triangle has all these interesting little things about it. Maybe I'll make a video about some of those things in the future. But this is how these things get expanded. Now, the difficult part of the binomial of expanding like a higher degree binomial like this is to get what those coefficients would be, because you're going to do all these multiplication, you have all these terms laid out, and you can get and then you have to combine those terms to figure out how many of each kind of term there are if they match. And so what we can observe here, if we look at this, right, if we look at the second degree polynomial, if we look at a, okay, the a term here, this degree is 2, that's the original degree. And then degree of a here is 1. And then technically, sorry, I meant to write a 1 there. And then technically there's an a to the 0th right there. So we went from 2 to 1 to 0. And on the other side, for b, right, this is like having b to the 0 here. This is b to the first, and then we have b squared. So as the degree of the a term starts high, so a like starts high, goes low, and b starts low, goes high, kind of, right? And so the next one, the coefficients, we can get this off of Pascal's triangle. Then we start with the a term, and it's a highest degree, it's the nth degree. Then we decrease that degree by 1, decrease that degree by 1, and then a 0, decrease that degree until it's 0. With b, this is b to the 0th, then we increase it by 1, increase it by 1 again, increase it by 1 again until it's up to n. And you can notice that pattern happening for all of these things. So this is how you can kind of, you can use the knowledge of Pascal's triangle and this pattern that we see to expand a binomial much more simply than just taking a binomial, multiplying by itself like 3 or 4 or 5 times. So let's do an example here where it can really help illustrate how useful this is. Okay, the first thing is we're going to use Pascal's triangle here, and to generate Pascal's triangle, you start with a 1, then the next row is a 1 and a 1, then the next row is a 1 and then a combination of the 2 above it, so 2 and a 1, and then a 1 and the combination of the 2 terms above it, so a 3, I get addition of the 2 terms above it, 2 plus 1, 3, and then a 1, and then a 1 and a 4 and a 6 and a 4 and a 1. And we know which fourth when we have a fourth degree polynomial, it starts off, this is a plus b to the 0th. This is a plus b to the first, right? This line, this line. So this would be to the second, this would be to the third, and this would be to the fourth. So these are the coefficients that we're going to be using for this expansion. And I like to go ahead and just write that right in first. So we're going to have coefficients of 1, 4, sorry, let me make that a little smaller. 1, 4, 6, 4, and 1. So so that's good. Now let's deal with the rest of it. So this here, this is like our a term, and this here is our b term. So we're going to take the a term, which was 2x, okay, and that is going to be raised in this, if we remember, right, we're going to start with the highest degree of 4. So that's to the 4th, and that's multiplied by the b term, 3y, to the 0th. And that's it. Plus, okay, your positives and negatives here are going to be dictated by the coefficients of what your quote-unquote a term and your quote-unquote b term are. Okay, now let me just quickly establish. So I'm gonna have the b term be in green. Okay, so now for the next term, we know the coefficient's 4. That's why it's there. And then we're gonna have 2x, and now we're gonna decrease the degree by 1, so it's gonna be to the third. And then we are for our b term, 3y, we're gonna increase the degree by 1. So from 0, it's to 1. Plus. Okay, then the next term, 2x, we were at 4, then we were at 3, so this one's going to be squared. B term, it's going up every time, so we're at 0, 1, this will be 3y squared. Plus, then we have the a term, 2x, it was at 2, now it's down to 1. And we have the b term, 3y, it was at 2, now it's up to 3. Okay, plus, and lastly 2x to the 0th power now, and b 3y to the 4th. Okay, so obviously we're not done. We have a little bit of math to do here, but everything's mostly taken care of. All we have to do really now is multiplication and take care of the exponents. So to do that, right, what is 2x to the 4th? Well, 2 to the 4th is 16, and x to the 4th is 4. 3y to the 0th, this is just 1. Right? Anything to the 0th power is 1. So this first term is just going to be 16x to the 4th. That's it. Plus. Now 2x to the 3rd, that is going to be 8x cubed. And then 3y to the 1st is 3y. So what is 8x cubed times 3y? Well, it's 24x cubed y. Then all we have to do is say, what is 24 times 4? It's 96x cubed y. Okay, next. 2x squared is 4x squared, right? It's 4x squared. 2x quantity squared, right? That's the same thing as saying 4x squared. 3y squared, that's like saying 9y squared. And then times 6. So what is 6 times 4 times 9? 6 times 4 times 9 is 216. So this is 216 is a coefficient, right? 6 times 4 times 9. And we have x squared, y squared. Then we have plus. So now what is 2x to the 1st? It's just 2x. 3y cubed, that's 27y cubed, times 4. What is 27? What is 4 times 2 times 27? Well, it's also 216. So 216x y cubed plus, and then lastly, so that's just 1, right? And then 3y to the 4th, that's going to be 81 y to the 4th, and it's times 1. So 1 times 81 is 81 y to the 4th. So there we have it. That is our answer to this. That is how we would expand, like these things here, they're equal to each other. And it was a much less labor-intensive process than going 2x plus 3y times 2x plus 3y, ... You could, I mean, it's not that bad, because you could get a quadratic here and then multiply it by itself. So it'd be kind of like doing squared twice, same thing as fourth, right? So that is a very useful thing there. Okay, so that's super useful, knowing Pascal's triangle. is super useful for expanding binomials, for binomials that are within reasonable degree. If we, on the other hand, wanted to know something like what is a plus b to the 15th, like, and I wanted you to expand that, first of all, that's a horrible thing for me to do because that's going to be a lot of terms. There's going to be 16 terms in that expansion. But I want to know, how could I generate these values? Because if I wanted to use Pascal's triangle for this, I would have to write Pascal's triangle out to 16 rows, which is awful, okay? And so what we can do is think of another way, think of another sort of pattern for how these numbers in Pascal's triangle are being generated. And so what you can do then is look at these. So let's say I'm looking at this one right here. Well, how many different ways, if I start up at the top, how many different ways are there for me to get down to that 1? Well, I can go left, left, left. There's only one way to get to that 1. What if I wanted to get to like this 3? Well, I could go left, right, right. That'd be one way. I could go right, left, right. That'd be 2 ways. And I could go right, right, left. 3 ways to get to that 3. Okay, what if I wanted to get to this 4? Well, I could go left, 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 right. I could go left, left, right, left. That's 2. I could go left, right, left, left. That's 3. And I could go right, left, left, left. 4 different ways to get to that 4. So you're seeing that these numbers represent the number of ways that you can get from the top down to that term. And it's just a count. And when you hear the word number of ways, you might think to yourself, that is just, that sounds like a combination. So if you've done probability before, you would know that the word combination implies it's talking about the number of ways that you can do something. Like, for example, the number of ways you can come into the first 3 positions in a race, or something like that, if it's a race of like 8 people. Okay, so what then we can do is say, all right, well, what's the pattern? How would we generate these numbers? And the way you can do that is to say, all right, we could call this is the 4th row, right? This is row 1, 2, 3, 4. But it represents the expansions for 3rd degree polynomials. Okay, and so if we do, sorry, 3rd degree binomials. So if we wanted to, for example, get this 3, how could we use the nth? So it's the nth degree. So this would be like a plus b to the 3rd, right? And the coefficients of that expansion. So if this is our number of like things, and we want to choose, how do we get to this one? Well, it seems like so if you know anything about combinations, like if we did 2 choose 0. Well, if you got 2, there's 2 things. How many ways can you choose 0 of them? 1, you don't choose any, right? So mathematically, the way that works is 2. By the way, the other way you write this is 2 choose 0, because it is the same thing. Okay, same thing as 2 divided by. So let me just clarify. The way this works is if we have combinations, and you don't need to know this right now, but you would do it by n factorial, or n factorial divided by r factorial times n minus r factorial. Okay, so if we have 2 and 0, we got 2 factorial on the top, 0 factorial, which is 1 on the bottom, and then 2 minus 0 factorial. So we'd have 2 factorial or 2 factorial, which is 1. There's one way to choose 0 things from 2, right? That's how. Okay, then, so this is 0, so that means this should be 2 choose 1. So if we're right about that, then this would be 2 choose 1. Ooh, sorry, there's no line there. I get that mixed up all the time. 2 choose 1, that should be 3. Let's see if it is. So we got 2. Wait, did I do this wrong? We did. Oh, we're doing the 3rd degree. I don't know why I had that there. Sorry. This would be 3, right? When I was doing this before. Okay, so now we're on the 3rd row. So this 3 choose 1. 3 choose 1 should be 3. Okay, so this is going to be 3 factorial divided by 1 factorial, which is 1, times 3 minus 1 factorial. So that would be 3 times 2 factorial. 1 factorial is just 1, don't even bother with it. And then 2 factorial. So that's cancels, and it's 3. And would it work for any of these? So if we wanted to find if it worked for this 10th degree, for this, sorry, this 10 down here, well, this was 3rd degree, this was 4th degree, so this would be a 5th degree. So this would be the 0th, 1st, and 2nd term. So how many ways? So if 5 choose 2 is equal to 10, we're golden. Okay, so let's see. If we have 5 factorial divided by 2 factorial times 5 minus 2, which is 3 factorial, well, okay, so that's 5 times 4 times 3 factorial divided by 2 factorial times 3 factorial. Okay, that cancels. So we have 20 divided by 2 times 1, and it's 10. So this works, and what that allows us to do, if we use this idea and combine it with the way that we saw exponents decreasing for A, right? As we go down the list, exponents are decreasing from n to 0, and the exponents for B are increasing from 0 up to n, and combine it with this thinking, then what we get, oops, sorry, that went way too fast, we get this kind of formula, this general formula for a binomial expansion. And so this is better than, well, it's not better, but it might be more useful in a lot of cases than just Pascal's triangle, because if we wanted to go with a really high degree expansion, we can basically plug it into this. All this is here is just a way to kind of generalize what the binomial expansion theorem is when we use Pascal's triangle. So you can see this is those combinations that we were getting off the triangle, where n is the nth degree. Okay, and then look, so we start at the nth degree, then we go down 1. This is the A term. It starts at n, goes down 1, 2, and keeps going down until it's 0. The B term starts at 0, keeps going up until it's up to the nth term. And so that is the binomial expansion theorem as a formula. And there's one other useful thing here, and that is if we wanted to find a specific term of a binomial expansion. So we had a problem earlier where it was 2x plus 3y to the 4th. If I wanted to, instead of going through the process of doing the entire expansion, if I wanted to know, like, what is the third term of this? Well, so I'd be looking for r, in this case would be 3. We can say that we can get this directly, and this is just straight up off of that previous formula, where we can say, all right, if I want to know this, then I'm going to find it's the 4th degree polynomial, right? So n is 4. It's 4, and then if I'm looking for the third term, I'm going to put 2. So it's 4 choose 2 in my combination, and then it's going to be a, which was 2x, to the n minus r minus 1 power. So n is 4, right? 4 minus, and then r is 3. So r minus 1 is 2, right? So 4 minus 2. Okay, that power, and then times b, which b was 3y, to the r minus 1 power. We just said it was 2. And so now we can do this. Well, what is 4 choose 2? Well, it's just this, right? So it's 4 times 3 times 2 factorial divided by 2 factorial times 2 factorial. So what is 12 divided by 2? It's 6, right? So that coefficient is 6. So this is 6, and we know that. We could have got that from Pascal's triangle. Okay, times 2x to this 2x squared, 2x like quantity squared, times 3y quantity squared. So that was 6 times what would be 4x squared times what would be 9y squared, and we get 216x squared y squared. And you can go back and see, is that the third term of the expansion that we did with Pascal's triangle? And you'll find that it is. So this is a really useful thing to know here as well.